Ma'am, we are live now.
Yeah, okay. So, participants, I welcome you once again to this 10-week long program on learning physics with conceptual and problem-based approach organized by the National Academy of Sciences India Delhi chapter. So, our first speaker of the day, Dr. Ashok Kumar, he has already joined us and he is going to illuminate you all with his expertise on thermal physics. So I would like to give a formal introduction to Dr. Ashok. Dr. Ashok Kumar is a senior associate professor of physics in Ramjas College, Delhi University. He did his MPhil and PhD from DU. His PhD research work was on solar energy and it was in collaboration with IIT Delhi. He has teaching experience of more than 27 years. He has taught at Eritrea Institute of Technology, Eritrea, and also worked as HOD Physics Department. He was also appointed as Professor of Physics at Addis Ababa University, Ethiopia, selected as a UGC Fellow for Hungary, selected for faculty position at Zambia, and was appointed as a Principal of Government College in Bihar. He has several publications in reputed referee journals, including conference proceedings. He is also author of 4 books on optics, thermal physics, and statistical mechanics. He has delivered several talks and presented several research papers in national and international conferences. He has been associated with a number of organizations like Commission for Scientific and Technical Terminology, Government of India, UGC, KVS, SSC, NU, DST, etc. as a subject expert, resource person, and advisor. He was also PI of 2 innovation projects. He has been involved in various committees and organization of many events. So, Dr. Ashok, you're most welcome, and I request you to kindly start your presentation.
Thank you, madam. Should we start?
Yeah, you have started sharing, but it is visible now. It is visible.
Oh, okay. Thank you, Dr. Pushpa Vindal. Thanks a lot, and thanks to Dr. Savita as well, and Dr. Yogesh. Now, I start with the other topic. Welcome to all students. Very good evening to everyone. And today, yesterday we have covered the entropy, basic concept of entropy and related matters to entropy. While completing it, I observed that some of the questions were coming on the chat box from the students, but due to shortage of time, I could not cover. But and promise that today I will address those problems. So before coming to the next main chapter, let us see some of the problems, typical problems, in the sense these problems would be representative problems, because there is no limit of problems in any chapter or on any topic. The only thing that particularly I emphasized on the important clues by which you can solve the problems that I have already given yesterday, in which you find that one such clue or important formula is related to the entropy change during a melting process, or change of state, or vaporization change, or temperature rise change, okay, etc., etc. So let us, and at the same time, if you recall that there were 2 processes, isothermal and adiabatic processes, in which the PV diagram and TS diagram also we discussed. Now, one such question which was asked earlier also could be the, suppose question number 1 we are taking up, which of the 2, an isothermal or an adiabatic, has greater slope. That means they want this, the degree of slanting of 2 curves would be greater, and they want the justification behind this. That means you have to answer it mathematically or prove it mathematically. So an adiabatic curve will have greater slope uh, compared to the isothermal. Now, this could be a student can answer by just listening or by some other hint he or she has got. So the proof for the mathematical support behind this is for isothermal process, the PV is equal to constant. Actually, it is PV is equal to n RT, and if n is 1 and R and T, because isothermal process, so T is also constant, so PV is constant. So if we differentiate it, we get PV is equal to constant, we get PdV plus VdP is equal to 0. Okay. So from here dP by dV, which is actually the slope, because it is the PV diagram. So change in pressure with respect to change in volume, corresponding change in volume. This ratio gives the slope. So it is minus P by V. Similarly, for adiabatic process, PV gamma is constant. So if we differentiate, we get this expression gamma PV gamma minus 1 dV and plus V gamma dP is equal to 0. So from here we get dP upon dV is equal to minus gamma P upon V. So here we see that this gamma is a multiplication factor which is coming for the slope. Okay. Now we know that this gamma is the ratio of the specific heat at two situations, that is specific heat at constant pressure by specific heat at constant volume. And for monoatomic, diatomic, and polyatomic or triatomic gases, the values are 1.2 to 1.3 and 1.4 something. I don't remember exactly, that you will find it, but it is certainly greater than 1. Therefore, you can very easily understand that this dP upon dV is greater in case of adiabatic process. So this is the mathematical support. One year uh, this question was asked, and we can say with mathematical proof that the slope and adiabatic process or adiabatic curve is gamma times greater than that of the isothermal. Now, the second problem is 1 kilogram of water is heated from 0 degrees Celsius to 100 degrees Celsius and converted into steam at the same temperature. Now, uh, steam at same temperature means the steam temperature is 100 degrees Celsius. Uh, Here, sometimes students get confused that the steam temperature should be 100 degrees Celsius. No, not necessarily. Try to understand when there is conversion of one state to another state, the temperature remain constant. That means as long as the water gets converted into steam or vapor, the temperature will be 100 degrees Celsius. But the temperature of steam can further be raised, which are called the supersaturated vapor or super uh, heated, super hot steam. So that is possible. Uh, Therefore, here it is specified that the vapor is or the steam is at 100 degrees Celsius, not more than that. Now it is the question is calculate the increase in entropy, and when given the specific heat of water is this, the value is given, and latent heat of vaporization is also given. Now we have two specific heat. I'm sorry, two entropy changes. One entropy change which is due to the rise in temperature, because it will be from 0 degree Celsius water getting converted into 100 degrees Celsius water, and the other is the change of state. That means the when it will get converted into vapor. So the first delta S1, if we consider, so MC formula will be there, but we have already solved it. That is what I wanted to emphasize here, that yesterday those important formulae we have already I have already told you and uh, expressed there. So MC log T2 by T1, okay, And from there, if you put the values, we find that it is coming out to be 1305 Joule Kelvin, okay, per Kelvin. And the other one is entropy changed while there is conversion of steam, conversion into steam. So that is ml upon t, and this is 6.06 into 10 to the power 3 joule per Kelvin. So total will be the net change, entropy change will be, that will be increased because that all both the quantities are positive. So it is delta S is equal to S1 and S2, and finally it is coming out to be 7365. So this kind of small problems, which is based on simple the formula that we have to keep in mind, and we can solve such kind of problem. Similar problem is here, slightly different. This was also asked in university exam 1 year, but here there is a small uh, degree of difficulty is slightly more, because it says that the specific heat at constant pressure is varying by a relation Cp is equal to 0.4 T minus 0.05 T square minus 0.25. Okay, in the temperature range 50 Kelvin to 100 Kelvin in calorie per Kelvin. Okay, the unit is given. If 4 moles or 4 molecules of the material, uh, gram molecules of the material or the substance is heated from 50 Kelvin to 100 Kelvin, calculate the change in entropy. Now here we need to find out basically what is the value. We have to solve this because Cp does not remain constant, Cp is varying in this temperature. So how it varies? So delta S is integral over delta Q or dQ upon T, and this is the integral is from 50 degree to, I'm sorry, 50 Kelvin to 100 Kelvin. 4 is mass. Okay, this dq value mct formula we have to put over here. So 4 into cp dt upon t. But in place of dt, we have in place of this dt, this cp formula we have to put the whole here like this. So here this can be solved as like this, the 4 being constant, we keep it out, and integral over this. Now if we divide it by t, then this becomes 0.4 minus 0.05 t, and here the square cancels out by t, and 0.25 by t dt. If you solve it, this integral, okay, integration, if you solve, you get minus 640.69 calorie per Kelvin. So here you don't get confused by how this entropy became negative. That means there is a decrease in entropy. Mind it, there could be decrease in entropy, but the entropy of the whole system can never be negative. This entropy decrease, this entropy uh, uh, I'm sorry, this comes out to be 670.69. 670. This is wrongly written. Okay, so minus 670. This is not 640. It is actually 670.69 calorie per Kelvin. Please rectify it. This is wrong because when I prepared the the PDF, this was wrongly written. It is 670. Okay, doesn't matter. When you will be solving it, you will certainly put the right answer. Okay. So now one thing, yes, what we were discussing, that how this negative sign do come. So it does not mean there is decrease in entropy violating the Clausius rule or something. No, it is not violating, because as we have already seen that when the heat is taken from a source, the entropy of the source decreases, and when About the working substance, the entropy remains constant because it is cyclic process. The system comes back to its initial state. There is no change in temperature. Therefore, internal energy remains constant and therefore entropy as well. But when it is rejected to uh, the sink, there is increase in entropy, and the net entropy is in reversible process is equal to 0. If it is not reversible, it increases. So here this negative sign only shows that it is a part of the universe. That part could be anything. It could be source or something. So therefore, you should not get confused here. Now, similar problem is this, that so this is one kind of typical problem what we did earlier, the formula I had explained earlier yesterday. Now this problem, an ideal gas is confined to a cylinder by a piston. Okay, the piston is slowly pushed such that the gas temperature remains at 20 degrees Celsius. That means the process is isothermal. Okay, temperature remains constant. So heat is allowed to be exchanged. During compression, 730 joule of work is done on the gas. Find the entropy change of the gas. So here the energy is imparted in terms of work, not heat. All right, but certainly this work will, what it will do, this work will be imparted to the system or the working substance, and the internal energy of working substance will increase. Okay, and that will lead to increase in total energy and entropy as well. Okay, so now the size of the content on the screen is all right. Is it okay? Students, please respond. Okay, okay. So now here you see. So dq or delta q is equal to delta u plus delta w, the first law of thermodynamics. And as we know that the process is isothermal, because I already it is explained in the beginning, so very slowly it is pushed. Therefore, there is sufficient time to exchange of energy and temperature remain constant. So for isothermal process, delta U is 0. So whatever the total internal energy remain constant. So whatever heat is, that is due to the work. Here it is opposite. Whatever heat, it is not getting converted into work. Rather, it is the work which is getting converted into heat as internal energy or something. Okay, so this is equal to 730 joule. All right, because it is compression and system is not doing work, rather you are doing work on system. So if you recall, in the very beginning of different kind of processes in thermodynamics, the understanding thermodynamics is for the purpose of, or heat engine is the purpose of exploiting work out of energy, out of heat. So heat given to a system is always taken as positive. Heat taken from the system is taken as negative. Work done by the system is taken as positive. Work done on the system is taken as negative. So here the work is done on the system. Therefore, 730 joule is the negative work, uh, because we have done work on the system. And yes, is it all right? Yes. So now, uh, and this becomes, because we have already understood that this work gets converted into raising the in energy of the system, which is equal to delta Q. So delta S is delta Q upon T, which is minus 730 joule upon 293 Kelvin, because 20 degrees Celsius is there, convert it into absolute scale or Kelvin scale. So we have minus 2.49 Joule Kelvin. So this is the answer. So that is how very simple problem, but these all problems have two, three conceptual things that what will be the internal energy if the process is isothermal, what will be the other energy or other terms if the process is isothermal or adiabatic depending on the situation. Now come to another problem. This problem is based on the change in volume. If you recall that entropy change in terms of are you getting my voice or not? Am I audible?
Yes, sir, you are audible, sir.
Okay, okay, please. Because someone told me that it is not. So now, one problem is 1 gram mole of a perfect gas expands isothermally to 4 times its initial volume. Assuming complete conversion of heat into work, calculate the change in its entropy, given the value of universal gas constant is equal to 8.314 joule per mole per Kelvin. Okay. Now this is the problem. So here this problem could be in different form also, doesn't matter. We have to understand how to solve it. The basic formula or the basic relations we have already discussed earlier. Here it is the 4 times, it could be double or something, okay, or it could be compression also. Uh, so here you see from equation, so the final volume, the volume initial volume is V1, then final volume is V2, which is 4 times of the initial volume. So we have relation V2 is equal to 4V1 and the Q becomes W. That means we assume that ideally all the uh, heat gets converted into work. Okay. So now W is equal to, for the complete process cycle from V1 volume to V2 volume PdV, and PV is equal to RT, we already know. Therefore in place of P we write RT upon V, and RT being constant because isothermal process is there, so we take out RT from out of integral, and V1 to V2 integration over dV upon V. So which after solving we get RT log natural log E V2 upon V1. So we can say that V2 is 4V1, so it is cancel, the V1 cancels out, so W is equal to RT log E 4, which is this. So if we solve it for ds, then dq upon t, which is actually W, because dq is this is only the formula, but this q is actually the work in terms of work. So this comes out to be 2 point this expression divided by t cancels out. So finally we get 11.5265 or 11.53 joule per Kelvin. So this is the change in entropy. So meaning by such kind of problem, typical problem one of different formula, I have tried to give one exemplary problems for each formula, but you can solve simple form problems like this from other sources also. And if time permits, at the end I would like to give some other problems also. Now this is all about what we had left yesterday, because some students pointed out that it would have been better if some problems could also have been addressed uh, yesterday. But time was not there, so I preferred to complete the topic first, and then it will address the other problems. Now, today we are going to start another important topic which is interesting, which is completely new I understand that many of the students must have gone through it, but for those who are not very familiar or not have studied properly in this topic, they can get benefit out of it. I hope so. Now, this is thermodynamic potentials and functions, and at the same time, Maxwell's thermodynamic relations. Now, there are two approaches in learning Maxwell's equations or Maxwell's relations. One approach is very much like a mathematical approach in which what we do, we basically we take help of the partial differential equation, solve the partial differential equation of in mathematical form, and then we have constants and variables. We put the value of variables as one of our thermodynamic parameters. Okay, and then we get the relations. The other approach is first introducing the potentials, and then with the help of mathematical tool, we arrive at different Maxwell's relations, different equations which are Maxwell's relations. I prefer this method in the sense that the purpose of understanding these the Maxwell's four relations and potentials and functions from physics point of view, because basically our purpose is to understand the physical phenomena that are taking place inside a thermodynamic system. What actually is taking place? Okay, so arriving at result sometimes may not give you the intermediate understanding of the system, what is actually taking place. So that is why I feel that this method or this approach is more close to the understanding of physics than the other one. Okay, so let us begin with this approach. Now you know that any thermodynamic system, first of all, what is thermodynamic system? Any system which can be which is in the form of solid, liquid, or gas, preferably the gas, because where the effect of pressure and volume can very easily be understood, and the thermodynamic system can be represented by different coordinates or different parameters. These coordinates which can be measured from external sources are called extrinsic parameters. Okay, provided they depend on their masses. All right, and if the and they are also called observable parameters. These observable parameters could be of intrinsic nature and extrinsic nature. Intrinsic parameters are those which do not depend on the mass. For example, if you take the temperature of any system, so temperature, if you just half the total amount of the gas, the temperature will remain the same. Okay, therefore we can say the temperature is intrinsic parameter, intrinsic variable. Similarly, if we take density, whether we take a small amount or large amount of the total system, okay, this is not going to change. But similarly, the pressure is not going to change, whether the pressure of any small section of the whole system we take, or the whole the bigger section we take, the pressure will remain the same. But it is not true for other parameters. For example, volume, if we just half the mass, the volume will also change accordingly. So these are certain things. Now the important thing, the relevant part is that a system can be represented by certain variables, and these variables, common variables, are pressure, volume, temperature, entropy, internal energy, etc., etc. Okay. Now, here homogeneous system means a system which have the similar property of density, similar property of composition, similar property of other parameters all over the system is are called homogeneous, otherwise non-homogeneous or heterogeneous system. Now, for example, if we take PVT and S, that is pressure, volume, temperature, and entropy, as four variables. We select, suppose, that the system is being represented by these these four parameters or variables. Now, out of these four, if we take any two are known. These any two will give you the other two. That means the chosen two may vary independently, but they are giving you other two. This can be understood like this. If suppose we have a cylinder and piston arrangement, and or the simple ideal gas equation, PV is equal to RT, where R is constant. So variation of PV will actually indicator of T, or if it is isothermal process, then PV is equal to constant. So basically the variation of volume indicates pressure. So just by change of volume is indicator of pressure. All right. Similarly, in this case, if we know two, and these two may be independently varying, but these two can give information about other. So we say that the two are which those two which have been chosen are actually the variables, and the other two which these two will give as an information will be called as their functions, because they depend on it. This will be elaborated later on in a better way, so don't get disheartened at this moment. Okay. Now, so meaning by that, out of four, if we take two, the other two are, there exists some relation between these four, right? So these first two and their functions, two other functions. So there is some relations. This can be illustrated here by this example. Let us take first law and second law. The first law says dq is equal to du plus pdv, and the second law mathematical form is dq is equal to tds, that is TdS relation. So if we combine, TdS is equal to du plus pdv, and therefore uh, du is equal to TdS minus pdv. Okay, so this is TdS is actually the heat energy form, and pdv is the work energy form. So internal energy is the difference of the total energy minus work energy. All right, now here you see very interestingly that the change in internal energy, this du is change in internal energy, is internal energy of the system is a function of, or it can be expressed in terms of four parameters, four variables. What are those? These are temperature, these are entropy, pressure, and volume. All right. So we can say that this change in internal energy depends on or functions of temperature, entropy, pressure, and volume. Four parameters. Okay. So for a complete knowledge of the system, all right. So here you see, you could understand that the one parameter when or two parameters we select, the other two parameters we can find out. We will see how it is possible. So for a complete knowledge of the system, certain other relations are also required. For this, we introduce some functions of the variables P, V, T, and S. That is what we want to. We don't know right now what are those functions, how they depend on these parameters. And we will examine it, whether this statement is true or not. So those functions of the variables as PVTs, and their functions are called potentials or functions. All right. So there are four basic or principal thermodynamic potentials, okay, and which are important for the equilibrium state. So we will take up one by one. First, we will define one such potential. We define it. Okay, define in the sense that we give the name, or we give the name, and we, on the basis of their properties, we give the name, and then from the definition we find the relation, and then take their dependence as potentials. So first such parameter is internal energy. First potential is thermodynamic potential. This potential, the name is potential. Why? That also we will examine later on, why this name is thermodynamic potential. Because we are familiar with the electric potential, we are familiar with gravitational potential, magnetic potential. Why this thermodynamic potentials? That also we will examine. So internal energy or intrinsic energy, of course this intrinsic energy is a term which is often used in electronics or solid state physics, and internal energy in thermodynamics or elsewhere. So internal energy is the energy contained in a substance or in a body. Total energy contained in a body is called its internal energy, and it could be made of two energies. One is internal energy due to potential, and internal energy due to kinematic. So potential energy, potential internal energy, kinetic internal energy. Now, if uh, when the system goes from one energy, one state to another state, the internal energy changes, and it changes basically due to temperature. But, and at the same time, you know that the internal energy is a state function. For example, the potential energy is a state function. It does not depend on the path by which it travels. It depends on the initial and final position. Similarly, the internal energy only depends on its temperature, irrespective how the system has come via which route. That is not very important. So du is dq minus dw, and we know that dw is external work, which is pdv, and dq is tds. So du is equal to tds minus pdv. So this is fourth relation. Let me one thing here I left, I think. Yes, all right. This du is independent of the route between the two states, and du is given by dq minus, this is first law of thermodynamics, dq minus dw, and if we elaborate it, so du is equal to tds minus pdv, equation number 5. Now here you see, in this relation, du is equal to tds minus pdv. What are the variables? Du itself is a variable because it is a state function. It will vary, or it is a change, perfect differential change. But here you see, this t is constant and this p is constant. What is varying? The varying parameter is entropy, and varying parameter is volume. All right. So you can say that this u is a function of entropy and volume. Is it clear? U is a function of, because this du, which is a variation, will depend on the variation of these two parameters, S and B, where T and P are behaving here as constant. So that is why we have written u is equal to u s v, or u as a function of s and v. Now if we take its derivative, that means du derivative for changes ds and dv, so in s and v respectively, so can we write du is equal to, now for this, how we can, when the variation is, when the variation is dependent on two parameters, so we can express it in partial differential form. So what we do in partial differential form, we differentiate one, this in terms of the first one, okay, and keeping the other constant, and again with respect to the second one keeping the first one constant. So here you see the du can be written as partial taking partial derivative of u with respect to s keeping v constant ds, and partial derivative of uh, u with respect to v at constant s. So del u upon del s at constant v ds plus del u upon del v at constant s dv. So this is a standard form, mathematical standard form, which is equation 6. Now here you compare equation 6 and 5. The du is given as tds and minus pdv, and du is del u upon this expression. So here this ds is ds, so t is replaced by this and p is replaced by this. So can we say that the partial derivative of u with respect to s, that means change of internal energy with respect to entropy at constant volume, is nothing but the temperature, and change in internal energy with respect to volume at constant entropy is nothing but the negative sign of P. It is P. Only thing that it says that it will, when it will increase, the this quantity will increase, it pressure will decrease. If it is decreasing, pressure will increase. That's all. So only the sign indicates the direction, but it is basically the pressure. Now very interesting that the u variation of one very unique parameter is with respect to other is nothing but the temperature. You can say otherwise also, what, that if we know the temperature of the system, we can say for this situation, we can say that this is equal to the rate of change of internal energy with respect to entropy at constant volume, which is otherwise very difficult to find out. Similarly, if we know the pressure, we can say the internal energy change, how the internal energy changes with volume at constant entropy. How the constant entropy? Let it be an adiabatic process. So that means for an adiabatic process, change in internal energy by volume with respect to volume can easily be measured by just measuring pressure. So this is the beauty of this potential. Followed. So you see that the variation is giving you one information. This variation is giving you one information. Okay. So from here, the relation 7 gives connection of u with 4 variables. S, where is S? S, V, T, and P, out of which 2 are constant, 2 are variables. Okay. Here all are variables, but in this equation, this T, and don't get confused, sometimes I say it is 4 variables, sometimes I say that it is varying. Naturally here it is varying, but the variable itself behaves here as constants. T is variable, P is variable. In this equation, this T and P are behaving as constant, but not necessarily everywhere it will behave as constant. It will be varying at some other place, and S will behave as constant. So we will see it. Okay. So since du is a perfect differential, so we must have the condition for perfect differential, that if we alter the partial derivative, partial differentiation, del upon del v, del u, del s, v is equal to del upon del s, del u, del v, del s. This should be equal. This is a standard math every student must be knowing. Therefore, in this case, put del u upon del s at constant volume, which is nothing but T. So in place of this, you put T. So del T upon del V at constant S, as it was earlier, and del P, this del U upon del V at constant S is P. So with negative sign, del P upon del S into V. So here you see that this relation is del T upon del V at constant entropy minus del P upon del S at constant volume is called first thermodynamic relations of Maxwell, or Maxwell's first thermodynamic relations. It is not only Maxwell's relation, we need to specify Maxwell's thermodynamic relation, because Maxwell had given the relation, four relation in electromagnetism also. So those are called Maxwell's four electromagnetic relations or equations, and here four thermodynamic equations or thermodynamic equations. So what we did here, we first defined, first we understood how a system can be represented by variables. Then we saw that out of the four, if we select any two, then the other two may depend on these two. So the other two can be called as the functions of the first two. Okay. And these two totally depends on you what you are selecting. There is no such rule that which one you are taking. It is up to you. Now, thereafter we define first potential, that is as internal energy, and with the help of first and second law, we differentiated, and with the help of the mathematical tool, we came to knowledge of, we came to the equation, deriving an equation, this which is Maxwell's first equation. Now, out of which this Maxwell's first relation is important, at the same time we also have an important relation, that this partial derivative of certain physical quantity with respect to other quantity, keeping some parameter constant, is can be found out by the externally observable variables or parameter. Temperature, volume, pressure, these are observable parameters of any system. Okay, so this is an important information. Now come to the second function, second potential. This potential is called Helmholtz function. Now, what is Helmholtz? These are all scientists, and they are basically scientists in chemistry also. Okay, so Helmholtz function we define if we write first and second law combinedly. So du is equal to TdS minus dW. All right, because this is d cube. And if we consider a process in which the exchange of heat is allowed, exchange of heat is allowed means, when exchange of heat is allowed, that means temperature will remain constant, because heat is allowed to compensate the temperature. Because, all right, meaning by if the heat is coming out of the system, then the temperature should fall. But if heat, okay, and heat is allowed to compensate it. And similarly, if heat is put inside, then temperature will also rise. And if that is allowed to lose, then temperature will again fall. So this is basically isothermal process. So TdS, in which T is constant, right? So if T is constant, isothermal process, so can we write TdS as D bracket Ts? All right. So Tu is equal to dTs minus dW. Now here mathematics starts. So du minus dTs is equal to minus dW. So d, again two differentials. So du minus Ts is equal to minus dW. Let us define here U minus Ts. What is U minus Ts? U is internal energy, which is the total energy, and Ts is the energy which is heat energy. So if we subtract heat energy out of the total energy contained by the system, then we define it as Helmholtz free energy. Now this name Helmholtz free energy, this dF becomes equal to minus dW, where this dF, I'm sorry, this F is U minus Ts, and this is called Helmholtz free energy. Now the reason of this free energy is that from this relation dF is equal to minus dW, you see that it is with minus sign. That means whatever work you will be doing, it is at the cost of dF. That means if you are doing work on the system, so work on the system is negative, dF will be positive. That means there will be increase in free energy. And uh, if this is positive, this is negative. That means when the system does any work, so it is at the cost of the dF. And that is why it is called free energy, because this is exchangeable, or the work function, because this work function term also come in. Where do you find this work function? Where you find any student work function? Nobody is responding. Work function, photoelectric effect, very right. Correct, correct. So there the photoelectric effect, the work function denoted by phi, all right, because that is the energy. So h nu minus work function term was there. So at least that much work function is that minimum energy which is required to make the electron out of the metal, or out of the surface of uh, the metal, so that it will travel. So that energy is required. So that is why it is called work function here. So because dF is minus dW, shows that for a reversible change, the work done by the system is equal to the decrease in this function F. Okay, so it is at the cost of, we can say, this work is done at the cost of this dF. Now, whenever we say at the cost of, means they are reciprocal to each other. Okay. So F is equal to, now again come back to this. This is all. Now you can say this has relevance only to be acquainted or to understand this free Helmholtz free energy, nothing else. Till now we understood the, or we examine what is the Helmholtz free energy. It has no business with proceeding towards the Maxwell's relation. Now again come back for the Maxwell's relation, this old relation, F is equal to U minus Ts. Okay, so here you see F depends on the state of the substance only, and dF is a perfect differential. Okay, now why, how? State of the substance, state of the substance means internal energy, which is function of temperature, and the energy related with the entropy. So what is this? Is totally depend on the state of the system. So dF is equal to du minus dTs. So this is, if we break it, so du minus dTs minus sdt. Okay, but du is equal to TdS minus PdV. So expand it. So we find that this TdS minus PdV minus TdS minus SDT, and these two cancels out. So we have finally dF is equal to PdV minus SDT. So this is the work part, this is the heat part. All right. Okay, and both are negative. So f is a function of variables v and t, because p is constant and s is constant, so it depends on v and t. So f is equal to fvt. So this conclusion we have arrived at. Now we take the derivative. So if we take, because the two variables are there, so partial derivative we do take here. So taking the partial derivative, df is equal to del f upon del v. पहला को first we did, and keeping t constant and dv, and plus del f upon del t, the second one, keeping the first as constant, dt, 11th equation. Now if we compare 10th and 11th, so here we find that in place here, this is dv, here dv, so in place of del f upon del v at constant temperature is representation of minus p, and here del f del f upon del t, because it is coming at dt, is representation of minus s. If we put these two, so then we find del f upon del v as minus p, excuse me, and del f upon del t v is equal to minus s. Again, this is very important information in the sense that the variation of function with volume, and I'm sorry, I did not write here, it should be t here. This should be del f upon del v uh, at constant temperature, right here, T, okay, is equal to minus P, and del F upon del T at constant volume is nothing but entropy. So again, entropy can be found out with the help of entropy, otherwise difficult to find out, but entropy can be found out with the change in Helmholtz function with temperature. Okay, since Tf is a perfect differential, so their partial derivative with respect to each other must be equal. So del upon del v, del f del t v is equal to del upon del t of del f del v t equals. So using now equation 12, in place of this you put this p and put s as negative sign, so both negative will cancel out, so we have relation del s upon del v uh, at constant temperature is equal to del p upon del t at constant volume as this. So this is Maxwell's third relation. um, uh, Sorry, I forgot to write here. This is Maxwell's third equation. This is Maxwell's third equations. First equation, second equation, and this is Maxwell's third equations in thermodynamics. Please note down this one here. It should be the third equation. So 13 equation number 13 is Maxwell's third equation. Okay. Now the fourth potential we define here, another potential we define here as enthalpy or total heat. I'm sorry, this is second one. This is Maxwell's second equation. This is Maxwell's second equation. This is Maxwell's second equation. 13 is Maxwell's second equation. All right. Now, do you have, can I write here with a pen? Okay. So now, so students, please note down equation 13 as Maxwell's second thermodynamic equation. Now come to the third potential, which is enthalpy. Now this enthalpy is total heat. Enthalpy is a term which is very much common in use in chemistry or chemical engineering, and it indicates the total heat. Total heat. Now total heat means the internal energy as well as the work energy. All right. And you know that the internal energy includes the heat energy also. So it is an extensive and significant thermodynamic property, enthalpy. And there is one definition that enthalpy is that physical quantity which remains constant in adiabatic throttling process, which is basically Joule-Thomson effect. And mathematically, it is defined as H is equal to U plus PV. Now, because Helmholtz function we do not indicate by H, there is some standard which have been selected all over the world, so we cannot change it. Of course, these are variables, but we cannot change like this. For Helmholtz free energy, F is used. For enthalpy, we use H. All right, and for Gibbs function, G. We cannot change it just by the name Helmholtz function by H. No, it cannot be done. So, I don't know, you have read it, that the real gas behavior, in real gas behavior, you might have gone through Joule-Thomson effect, in which the ordinary gas is passed through a very high pressure and suddenly the pressure is released. It is passed through very narrow orifice or very fine tubes. These narrow orifices are uh, are made by pressing the cotton wool or glass wool very highly compressed. So we can assume that the highly compressed glass wool or highly compressed cotton or wool behave as fine orifice. Orifices are fine tubes. All right. Uh, uh, it is just like when the plants are, these are capillary tube, you can say. And in capillary tube, the narrowness is very high. Okay. The size of the tube is very less, and therefore it is not the capillary ascent, but when the gas passes through it, the pressure tremendously increases. So an experiment was performed by Joule and his student Thompson, okay, and in which it was found that what happens when gas is suddenly allowed to expand automatically, okay, and from very high pressure to it is coming to the atmospheric pressure, and it was found that the gas in many cases gets cool, and in two cases it was not cooling, but there was heating effect. Now, as the throat is pressed, so the pressure is increased and the gas comes out with a very difficultly it comes out. So this is called throttling process, as the throat is compressed. Okay, so this is also called throttling process. So in throttling process, what was observed that there was a decrease in temperature outside, but one thing was remained constant, because the decrease in temperature is decrease in internal energy. And it was observed that despite the internal energy and work etc vary, but the total energy remain constant, and that is called enthalpy. So that idea is one of the way to define enthalpy. Is what is enthalpy? So this is that physical quantity which remains constant during uh, an adiabatic throttling process. Adiabatic in the sense that heat exchange is not allowed. Okay, so forget about it here. Not more than this is required. So H is equal to the total internal energy and work energy. So now if we differentiate, we get dH is equal to du plus dPV, which is actually the du is TdS minus PdV. All right, because this is the total heat dq minus dw, and this pdv plus vdp. So this pdv cancels out, so we have tds plus vdp. All right, 14th equation. Now at constant pressure, dP is equal to 0, P is equal to constant, so dP is equal to 0. So dH becomes TdS, dH becomes TdS, and which is equal to dQ. So amount of heat given to the system from an external source becomes enthalpy, and that is why its name is heat function. Why we call it total heat or heat function? Because it is that heat which is supplied to the system. Okay. Now here from this relation what we find? So dH is equal to TdS plus VdP, means H is function of S and P. All right. So that is the conclusion. H is function of S and P, whereas T and V are constants in this relation particularly. This cannot be true everywhere, no, particularly in this case. So now if we take the derivative, so dH is equal to del H upon del S at constant pressure, ds plus del H upon del P constant S dP. 15. Now if we compare the equation 15 and 14, so in place of ds, okay, in place of ds we have here ds, so T is being replaced by, otherwise we should say that del H upon del S at constant P can be replaced by T, and del H upon del P at constant S can be replaced by V. So when we put it, so we find here del H upon del S, T is equal to T, and del H upon del P at S, constant S, is equal to V. Again, I would like to emphasize here that this variation, partial variation of certain quantity, why this, how we observe this partial variation of a quantity? It is not only mathematics, it is actually actually in practice taking place, where the chemical reactions are taking place. For example, if there is a chemical industry, so in chemical industry there are certain parameters which are continuously changing, okay, and the variation of such parameters with respect to other can easily be observed by, can easily be calculated just by observing the external variables like temperature, volume, pressure, etc. Okay, so this is an important, this could be of great use in finding the property of the material, finding the property of the chemical, etc., which can easily be measured with respect to, by just measuring the external observables like temperature, volume, pressure, etc. So we have finally, if this is the situation, we put there, and by placing, and at the same time, of course, this dH is perfect differential, so uh, their derivatives otherwise should be equal. That means this relation you understand. So we put this in place of dH, from there T, and from uh, dH by del P, S is equal to V. We have del T upon del P at constant entropy is equal to del V upon del S at constant pressure. So this relation is Maxwell's third thermodynamic relation. In a better way, we should say this is third thermodynamic relations by Maxwell. Okay. Now the fourth and last one we have is Gibbs potential or Gibbs free energy. So here also this free energy concept has come. Now it is again we mathematically define. You can say why we mathematically define. You see, it is Gibbs was a scientist, uh, and just we define and operate certain things, we come to very good conclusion. So that is the contribution of the scientist. If we do, we could also be called as famous, become famous. So students, here you see, so mathematically it is defined as Gibbs function is the enthalpy minus heat. Try to understand. It is enthalpy. Enthalpy is the total heat. That means total heat, internal energy heat, and work energy, both. And here it is the total minus the heat part. Okay, so we can say, because H is made of U plus PV and F is made of U minus TS. So if you substitute these relations here, finally you will get G is equal to U plus PV minus TS. U plus PV minus TS. Okay, if we differentiate it, so we have three uh, 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 combinations here. So dg is equal to du plus pdv plus vdp minus tds minus sdt. Okay, minus sdt. So this dq cancels out. So finally we have dg is equal to vdp minus sdt. So here you see. Uh, Now again, just to understand this Gibbs function, it has no business what we are discussing here, no business with derivation of Maxwell's relation, just to understand what is Gibbs function. So in an isobaric isothermal process, that means the process P is also constant and T is also constant. So naturally dP is equal to 0 and dt is equal to 0. So we can say that dg is equal to 0 or g is equal to constant. This is just conclusion which is used to understand as a property of Gibbs function. What is that? That the Gibbs function is that physical quantity which remains constant in reversible isothermal isobaric process. Is it clear? In an isobaric isothermal process, the Gibbs function remains constant. Now this could be one of the objective question. That parameter which remain constant during a reversible isothermal isobaric process. Gibbs function at enthalpy, internal energy, another something. All of the above, none of the above, like that. So this information is an important information from entrance point of view. So as G is equal to H minus Ts, and in an irreversible process, so if you recall, in an irreversible process, S increases, isn't it? We have already seen that the S remain constant during reversible process and S entropy increases during irreversible process. So think about the variation of Gibbs function in an irreversible process. What will happen? This S will increase. When S will increase, that means something is being subtracted from H. That means G is decreasing. So in one case, reversible process, G is constant, and in irreversible process, G is decreasing. That is what we concluded. G is constant in, I'm sorry, and in an irreversible process, the S increases and as a consequence, G decreases. So what we conclude, G is a constant in a reversible process. Of course, this reversible process is isothermal and isobaric in nature, and and G decreases in an irreversible process. That means G never increases. That is the conclusion, because we have only two types of processes, either reversible or irreversible. And in one case it remains constant, in one case it decreases. So it never increases. Whereas just opposite to it, the entropy either remain constant or increases, it never decreases. So here another question could be framed, that the two quantities which behave inversely or which behave oppositely with a point of view of increase and decrease are Gibbs function, entropy, entropy and enthalpy, enthalpy and Gibbs function, or something like that. The four options are there. you have to keep in mind. So that is the purpose, because uh, 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 if we uh, if we examine, or if we proceed one by one, taking one potential and examining the potential's property and then arriving at the Maxwell's relation, we have better understanding of physics, what are going on in between. Otherwise, deriving Maxwell's relation, because sometimes it is short also, easy also, if we proceed only by the help of mathematical tool. Now, if we take like this, so again these all are description from here upward, or before that we have just analysis of the Gibbs function from competition point of view I described. So now we come again back to G is equal to function of P and T. As we have seen here, G is function of P and T, because S and B, they are constant, behaving like this here. So here, friends, dg is equal to partial derivative. We take del G upon del PT dP and del G upon del TP. Here it behaves as gamma, capital gamma, it is T. So del G upon del T at constant pressure dt, equation 20. So compare equation 19 and 20. You will find that del G upon del P at constant T is nothing but the volume of the system. Okay. And del G upon del T at constant pressure is nothing but the negative sign of the entropy. So you see here also it is concluded, S negative, G positive, right? So G, whenever S will increase, so G will decrease, and S will decrease, G will increase. Since S will never decrease, therefore G will never increase. Finish. So now come back to, and dg is a perfect differential, so their partial derivative with respect to each other should satisfy this condition, and putting the value from this 21 in this, so we get finally here in place of del G upon del P T V and del G del P del T at constant pressure as minus S, we have del V upon del T at constant pressure is equal to minus del S upon del P at constant temperature. So this relation is Maxwell's fourth relation. So we have, this is 22nd equation. So we have four thermodynamic relations derived by Maxwell's great contribution, in the sense that we will find that these relations are of tremendous use, and we can study a number of such properties and unknown parameters or behaviors with the help of these four thermodynamic relations. So finally, we have, if we look at the conclusion aspect, so what we got? We have four thermodynamic potentials: internal energy, which are function of entropy and volume. We have Helmholtz free energy, function of temperature and volume. We have H enthalpy, function of entropy and pressure, and we have Gibbs function, function of temperature and pressure. So now these four are called thermodynamic potentials, because their variation with respect to some parameter is nothing but simple observable parameter. That is the beauty. And you can correlate like this. If you recall that, what is the relation between intensity and potential in a gravitational field? Gravitational field, the potential is rate of change of intensity with respect to distance, right? So you see, there it is called potential, because it is nothing but the variation of one parameter or quantity with respect to other. So that is called, so just for similarity, the name was given as potential. Okay, so finally we have these four potentials lead to four differential equations, and by solving four differential equations we get four Maxwell's relation as these 1 2 3 4, and with this we have the differential equation this, with this we have differential equation this, and so on. So it is difficult sometimes what to put constant and what to put variable. I would suggest, of course, even the Jimansky book and some other good book have suggested this relation. Good physicists have studied under very fine teachers. Okay, so this relation is given in which the one is variable with respect to other and keeping the middle one constant. So that I would suggest you go through the book and find the relation. It is interesting, not homework, but it is for your interest. You can find out so that you will not have difficulty in understanding and learning, memorizing these things. But nevertheless, the better way is just to know how to define the four parameters, nothing else. And out of which you know that two have been derived from the first and second law itself. Only the Gibbs function and Helmholtz function you define. Enthalpy is already very common from school time, you know, it is the total heat. Total heat means internal energy as well as work energy. Okay, so this is the only two form by which energy is transferred. So this is all about because Dr. Yogesh wanted some more time today. So I am finishing here. I hope next time we will be dealing with the application aspect, and in thermodynamic potentials and Maxwell's relation you don't expect that a particular numerical problem will come. Basically the it will be the deductions kind or some uh, other standard problem. For example, derive derive Clausius-Clapeyron equation using Maxwell's relation or something like that. Okay, so or uh, energy equation, second energy equation. What is second energy equation? Or just giving an equation, how it can be derived with the help of Maxwell's relation. So such kind of thing could be asked. Okay, we will try to see next time. Next time is tomorrow. Okay, thank you very much.
Thank you so much, sir, for giving out time to us and teaching the students so well.
Thank you. Any question? I would like to address a few questions in 2 minutes. If there is no question,
Students, if there are any questions, please write in the chat box. Sir,
even if you have any question, you can ask next time. Doesn't matter. I would always were these potential derived by Maxwell at the same time. Sir, no, that I don't know. I could not meet Mr. Maxwell, so that I don't know whether it was derived or not. You see, uh, uh, that I cannot say, and I think nobody can say it. That whether the potentials first they uh, first Maxwell derived potential, first they put potential or defined potential and derived Maxwell's equation. No, absolutely it is not so, because there are many uh, scientists who are of not the contemporary one, of different times. The other question is because throttling was involved in deriving them. So I thought, oh, it could be, but I'm not sure about it. All right.
There is one more question.
Mainly 4 parameters. No. You see, there are some other potentials also. There could be some other potentials also. There could be some other potentials also, but the thing is that in thermodynamics, we are concerned with these potentials. Okay. So, which are very much
Dr.
concerned.
Ashok, you have explained it so well that they've understood it all.
No, that I cannot say. It could be otherwise also. Anyway, thank you very much.
Thank you so much. Thank you for your talk. I think the students have really benefited from your talk. So thank you so much.
Welcome.
Yeah, I think Dr. Savita, you can stop recording and then you can start again.
Yes, ma'am.